Section 2.3, the limit theorems. Your essential question, what are the limit theorems and how do you use them? Now, before we get started and talking about these limit theorems, I'd like to address something that probably came up in 2.1. So for A here, it says show that f of 2 takes the indeterminate form 0 over 0. So this is probably a new term for you. And hopefully you looked it up either online or in the back of your book, or you did something to look it up. Nonetheless, I'd like to explain it to you and why it is called the indeterminate form. And what I'm going to do is I'm going to define that, or I'm going to compare it, I should say, with another term that you already know that we've used over and over and over, undefined. So I'm going to show undefined versus indeterminate, give you an example of each. I'll put maybe a little squiggle right here. So here's an example of something undefined. If I take 17 and I divide it by 0, that is undefined. Now I'm going to set that equal to q. Okay, and I'm going to show you why it's undefined. So I'm going to use cross multiplication because I have proportions here, or you can just think about, getting 17 by itself. Basically what I'm doing is I'm going to end up with 0 times q. Oops. I probably should use a capital Q because my lowercase q's are awful. But 0 times q is equal to 17. Now, is there any number q in this entire world that I can multiply by 0 to get 17? No. So there is no number that we can define for q to make this actually a true equation or a true statement. Okay, so that's why we call this undefined. Undefined means we cannot or we can't define any number in the whole wide world, q, for which this is true. Okay, now indeterminate. So in this example, they give you the indeterminate form 0 over 0. Because basically, if you plugged 2 into here, you're going to end up with 0 over 0. Now, that is one of many indeterminate forms. There are several indeterminate forms, and we'll get into that another time. But let's take 0 over 0 and set that equal to q. And let's see what happens when we cross multiply. So now I get 0 times q is equal to 0. Now, is there any number in the world that I can plug in for q, multiply by 0, and get 0? Yeah, actually, there's infinitely many numbers in the world that I can do that for. So we can't determine what q is, therefore it's indeterminate. Okay, so we can't determine, oops, my writing's getting very bad. The exact value for q, since there are infinitely many. Okay, now let's talk about our limit theorems. Hopefully that kind of cleared up for you the difference between indeterminate and undefined, and why this is an indeterminate form, but this is an undefined form. All right, so limit theorems. Now, these come from page 42. Let's see, let me turn to page 42. You should as well. So there's a whole page of limit theorems here, and I would definitely read through this. I always suggest that you read through your book. I'm going to kind of try and lay them out for you with some examples of each kind. So I'm going to lay out a few guidelines here. The first thing is that these limit theorems that I'm going to show you allow you to find limits by making substitutions. So you can actually plug in that input and hopefully get what the limit is. The next thing is, and we're going to assume right now that we're going to let g of x equal 2x plus 1 and h of x equal 5 minus x for purposes of our examples here. And so the following theorems are true if and only if the limit as x goes to c of g of x is equal to something. It has a limit. And the limit as x goes to c of h of x also has a limit. So there's some value there. We'll call this L1, limit 1, and limit 2. They may be the same number, but they may not be. Okay, so in other words, this is, I'll put AKA, the limit exists for both functions. I'll put all functions. No, I better put for both, for our purposes here. Now, these theorems can be extended to multiple functions. So, for example, the limit of a sum, I'm just going to use these two functions. I'm going to add these two functions together and take their limit. However, I could also do 3 functions. So the sum of 3 functions, or the sum of 4 functions, or the sum of 5 functions, okay? I'm just, to make this a little bit easier on ourselves, let's just do 2. All right, starting with our first limit theorem. It's the limit of a product. All right, so the first one here is, I will say the limit as x goes to c of the product of the two functions that we have established, g of x times h of x. And what I can do then is I can rewrite that as the limit as x goes to c of g of x times the limit as x goes to c of h of x. So I can actually take the limit of each individual function, and then I can just multiply them together. Okay, so let's do an example with what I've defined up here as my functions. So we'll go i.e. the limit, and I'll just choose as x goes to 3 of g of x times h of x. Well, I can really rewrite that as the limit as x goes to 3 of g of x times the limit as x goes to 3 of h of x. And so from there, I'll go ahead and I'll say, well, this is really the limit as x goes to 3 of, and we said g of x was going to be 2x plus 1, times, and then we'll do the limit as x goes to 3 of h of x, which we said was 5 minus x. And now from there, I can just substitute in this 3. And so if I substitute in 3 here, I get 6 plus 1 is 7. And then substitute the 3 in here, and I get 5 minus 3 is 2. So I get 14. So it's just a way to kind of make it a little bit easier. Could you have taken those two functions, plug them in here, or sorry, I should say here, distribute them, and then plug in 3? Totally. It's going to take a little bit more algebra to do. This was a little bit easier. Notice how I'm using the function or the limit notation. Make sure that you're using your limit notation, please. Okay, second property is limit of a sum. And this basically says that if I have the limit as x goes to c of both of my functions being added together now, Well, it's very similar to the multiplication one. So really this is the limit as x goes to c of g of x plus the limit as x goes to c of h of x. Okay, so using the two functions that we defined above, we can, and we'll go ahead and do limit as x goes to 3 again, just as a little example for you. If I wanted to do the limit of these two guys, I didn't give myself a lot of room here, so I'm going to go ahead and go down to the bottom. So this would be the same as the limit as x goes to 3, and g of x we said was 2x plus 1, plus, and so then I'll just add it to the limit as x goes to 3 of h of x, and we said h of x was 5 minus x. And now I just substitute in. So again, this is going to give me 7 plus 2, and I end up with 9. Hopefully you're seeing that this is pretty straightforward, pretty simple stuff. I think the hardest part that people struggle with is using the limit notation and understanding what that limit notation means. But the properties are pretty straightforward. If you're taking the limit of the sum of two functions, you can then just do the sum of the limits of each of those functions. So breaking it up. And the same, it's very similar with a quotient. So limit of a quotient. All right, so we've got the limit as x goes to c of a quotient like g of x being divided by h of x. So you can break this up too. So you've got the limit of a quotient could really be the quotient of the two limits, of the denominator and the numerator. So limit as x goes to c of g of x divided by the limit as x goes to c of h of x. So using our examples, using the functions that we defined above, we'll do an example of that. So again, I'll do as x goes to 3. The limit as x, that's an arbitrary number that I've picked out. Okay, could be anything. Of g of x over h of x is really going to be the limit as x goes to 3 of g of x over the limit as x goes to 3 of h of x. Okay, now I'll go ahead and I'll plug in my actual functions. So this will equal, let's see, where do I want to do this? The limit as x goes to 3 of 2x plus 1 divided by the limit as x goes to 3 of 5 minus x. Plugging in 3 for both of these, we have 7 and 2. So 7 divided by 2, or in other words, 3.5. Pretty straightforward. I'm hoping that you're finding that to be the case anyways. I think I'll go on to another sheet of paper for our next one. Okay, so our fourth limit theorem is the limit of a constant times a function so this would be, let's see, let me underline. I think I was doing that for all of them. So this would look like the limit as x goes to c of some constant, which we will call k, like 5, then times the function. And what you can then do is you can take that constant and you can pull it outside of the limit because that's going to stay the same. You're not substituting anything in for k. So this would really be the same thing as k times the limit as x goes to c of the function g of x. So in our little example, I'll do the limit as x goes to 3, and I'll use 5 as my constant, of 5 times g of x. Well, that's really, I'm going to then take that 5 and pull that out because that can go right in front of there. Because once I find the limit of g of x, right, because I can actually substitute something into that function. I can't substitute anything into 5. So just pull that 5 out. Say, all right, let's make it the limit as x goes to 3 of g of x. So this is 5 times the limit as x goes to 3. And we said g of x was 2x plus 1. And so I'm probably doing a lot of steps here, but this way you can see all the notation. And then we know that this is 7, right, because I plug 3 in and I get 7. So my final answer here is 35. All right. Fifth one, limit of an identity function. An identity function is just like, for example, like x. Okay, so it's just like, it's whatever variable you have, and you're plugging in that one variable. There's like nothing happening to that variable. So here, let me show you what that looks like. So the limit as x goes to c of x. Well, if I plug c in for x, I'm just going to get c. Or in other words, so for our little example, if I use the limit as x goes to 3 of x, well, that's just going to be 3. And it's that simple. And the last one's probably even easier because there's like nothing that's going to happen. So let's do the limit of a constant function. Okay, so this is like a constant function is like y equals 5. Okay, so if I do the limit, oh, and I'm not underlining. Why didn't I underline here? Just to be consistent. The limit as x approaches c of some constant, we'll call that k. Well, again, can I plug anything in for k? No, I can plug something in for x, but not for k. K is just like some constant, like 5. So it's just going to equal k. So for example, if I asked you to do the limit as x goes to 3 of the constant function 5. Well, you can't plug 3 in for 5. So it's just the constant function. This function, let's say, is like f of x equals 5 or y equals 5. Okay, so this is just going to be 5. That's all you can do. There's no variable to input. Okay, so hopefully you find those to be pretty straightforward, pretty simple, because now we'll do some problems where that maybe aren't so straightforward or aren't so simple. I'm going to go ahead and do that over here. So I'm going to start with example 1. Okay, so you're given f of x is equal to x squared plus x minus 6 all over x minus 2. And what you're asked to find is the limit as x goes to 2 of f of x. That's what we want to find out. Okay, so the first thing you always want to do is you want to try to evaluate, okay? So I'm going to do like little steps over here. So step 1, try to evaluate. So what I have is I have a quotient of 2 functions. And then within the numerator, right, I have the sum of 3 functions. One of them happens to be a constant. And same thing down here. So the first thing I want to try and do is I want to use my limit theorems. And I'm not going to write it all out right now using all the different, I'll do that in a minute using all the different theorems. I'm not going to explain exactly every single one that I use. But I'm just going to substitute. So I'm going to try and evaluate when x equals 2. Okay, so that would be the limit as x approaches 2 of f of x is equal to, and I'm just going to plug 2 into every single one of these. 2 squared plus 2 minus 6 all over 2 minus 2. And what you're going to end up with, well, that's 4 plus 2 is 6 minus 6 is 0 over 0. This is an indeterminate form. Well, guess what? We can definitely simplify this up here. Okay, so your second step now is to see if you can simplify. So try to simplify. Because by just substituting or just trying to evaluate, it didn't work out. I got an indeterminate form. Okay, so now I'm going to try to simplify. So we're going to have to use our algebra here. So remember, this can be factored, and maybe this is a factor of it. You can also use synthetic substitution or long division, totally up to you. Okay, I'm going to go ahead and use my factoring friends. So I see that there are factors of 6. That'll give me 1. So I'm going to go ahead and I'm going to factor f of x. So that's going to be the same as x plus 3 times x minus 2. And on the bottom, I've got x minus 2. Well, guess what? These reduce. Okay, so really now, I'm left with f of x is equal to x plus 3. Now at this point, I've got a simplified version of this, which basically tells me that I've got a discontinuity right here. Okay, it's going to be a removable discontinuity because these reduced out. Okay, the factors reduced out. If it hadn't reduced out, then I'd probably have an asymptote, right, at x equals 2. Okay, because I'd still have that denominator. Okay, all right, so moving on to our step 3, we're now going to use limit theorems to evaluate. So I'm going to say, well, okay, going back to the limit as x approaches 2 of f of x. And I've got the sum, really, of a function, of 2 functions. And then I'm also going to say, well, I'll get to that in 1 second. Okay, but basically I've got the limit of a sum. So I'm going to say, all right, this is really going to be the limit as x approaches 2 of x plus 3, which is the limit as x approaches 2 of x plus the limit as x approaches 2 of 3. And what have I just used here? Well, I just used the limit of a sum. They will ask you in some of your problems to write out every single property that you use or every single limit theorem that you use. So I'm just going to write that off to the side. Okay, and from there, let's see, I can plug 2 in here. Okay, so that's the limit of an identity. And then I can't plug 2 in there because that's the limit of a constant. So that's just going to give me 3. So now I'm going to have 2 plus 3. So this right here was limit of identity. This one was limit of constant. And all together, I'm going to end up with 5. Okay, we're going to do one more example. I'm going to use a clean sheet of paper. This one's going to, well, I write really big, but it takes up a whole page for me. All right, example 2, use the limit properties to prove. That the limit as x approaches 3 of x cubed, oops, not plus, minus x squared minus 2x minus 12 all over x minus 3 is in fact equal to 19. All right, so basically I'm going to focus on the most complicated side first. I'm going to focus on this left-hand side, and I'm going to try to make that equal 19. So first thing I should do is I should try to evaluate the limit, right? Try to evaluate. All right, so just this portion right here is going to be 3. Yeah, let's just do that. 3 cubed minus 3 squared minus 2 times 3 minus 12 all over 3 minus 3. This is either going to be undefined or indeterminate. So let's see what we've got here. We've got, this is 27 minus 9 minus 6 minus 12 all over 0. This is negative 18, negative 27. So it's 27 minus 27 over 0, or in other words, 0 over 0. Well, guess what this is? This is the indeterminate form. So I can't be done. Okay, I can't say, oh, it's just indeterminate, I don't know. So we can try and factor, okay? So we need to try and simplify this thing. So now we need to, let's see, how did I write it on the last one? Oh, try to simplify. Now, if I factor this thing, I notice that there's 4 terms, so maybe I can factor by grouping. If I pull out an x squared here, I'd be left with x minus 1. And if I pull out a negative 2 here, I'd be left with x plus 6. Neither one of those factors are going to reduce. So maybe I should go ahead and show you what I mean by what I'm doing here. I'm going to pull out an x squared here. I'm going to pull out a negative 2 here. And that's all over x minus 3. Does factoring work? Okay, so factoring will not work. So that's what I did here. That did not work. I always try factoring first, though. Well, another way that you can see if this can be simplified with a factor in the numerator is you can use synthetic division. So I'll do that. I will divide by 3, making sure that I have every single term accounted for, every single degree accounted for. So I'm going to do 1, negative 1, negative 2, and negative 12. In fact, x minus 3 is a perfect factor. So really, I can then factor this. I can say, all right, in the numerator, so let's rewrite this. The limit as x goes to 3. The numerator could be x minus 3 times what's left here, which is going to be x squared plus 2x plus 4 all over x minus 3. So now you can see I can simplify that x minus 3. So really all I'm doing is the limit of this stuff. So I have a removable discontinuity at x equals 3. Okay, again, if I couldn't reduce the factor in the denominator of x minus 3 with any factors in the numerator, then I would have had a vertical asymptote at x equals 3. Okay, so from here I'm just going to go ahead and use my, maybe I should, no, I'll leave it like that. Limit as x goes to 3 of x squared plus 2x plus 4. Then I'm just going to substitute now. Okay, so synthetic division worked, and my last is to, what did I write for my last step here? Use the limit theorems to evaluate. I'll abbreviate. All right, so then I'm going to end up with this right here. So really, I can rewrite this. Notice how I've got the sum of really 3 functions here. So I'll rewrite it as the limit as x goes to 3 of x squared plus the limit as x goes to 3 of 2 times x plus the limit as x goes to 3 of 4. Okay, so this is the limit sum theorem. Now really, this is x times x, right? So that's the limit of a product. So I can go the limit as x goes to 3 of x times the limit as x goes to 3 of x. Okay, and this right here, I just did limit of product. Plus the limit as x goes to 3, oops, actually, what do I have right here? I have a constant times a function, right? So I can actually create this as 2 times the limit as x goes to 3 of x. So this is a limit of constant times function. I'll put a times. Oops, I'm off the screen. I'm so sorry. Okay, so I went from the limit as x goes to 3 of x squared. Well, that's really x times x. So I use the limit of a product to rewrite that as the product of 2 separate limits. This was the limit of a constant times a function. So I brought that constant out because I can't plug 3 in for 2, right? So I'm just going to plug 3 in for 3. And that's the limit of a constant times a function. Okay, these are all properties that we've gone over. Let's see, where's that one? There it is. Limit of a constant times a function. And then this is just the limit of a constant. So I'm just going to go ahead and evaluate that already. So this is plus, that's just going to be 4. So that's just the limit of a constant. Okay, so I think now I can evaluate. These are just identity functions, right? Okay, so that's the theorem limit of an identity function. Basically, you plug 3 or you plug whatever in for x, you're going to get whatever that whatever is. That's c. Okay, so this is going to be, in this case, it does end up being, I should put an equal sign, ends up being 3 times 3, right? And those were both the identity, so limit of identity. Make sure you guys can see what I'm doing. Plus, and then this is going to be 2 times 3. And that again is the limit of an identity. So right here, limit of identity. And we already had the plus 4 from the constant. And so now I can just evaluate this. So let's say I got 9 plus 6 is 15 plus 4 is 19. And voila, it totally checks out. Right? That's exactly what we're supposed to do. We're supposed to prove that it in fact equals 19. I couldn't just do direct substitution because I got the indeterminate form. I always try factoring first because, well, factoring is usually easiest. But in this case, because my denominator was x to the first power, I was able to use synthetic division. Did that, I got a remainder of 0, which told me that x minus 3 was in fact a factor of the numerator. And then these were the remaining coefficients. And then I was able to use direct substitution by using those limit theorems to evaluate. And I wrote it all out because for this section, you're going to basically explain every single step you're doing. And there it goes. And after this section, we can take it down a notch with like explaining every single limit theorem that you used.